we have been discussing about vibrations of plates. So, we have looked at the rectangular and the circular plates in our previous lectures. Today, we are going to discuss some special problems in vibrations of plates. So, before we do that, now as you have seen in the previous lectures that even for some simple problems, the analytical solution becomes very complex, and sometimes with increasing complexity of the geometry or the boundary conditions, etc., the analytical solution becomes intractable. So, in such situations we would like to have approximate methods for discretizing the dynamics of plates and performing modal analysis, which we obviously expect them to be approximate, but then with we can, there is always a scope of improving the accuracy of these methods, and we have seen such approximate methods in this course. So, today we are going to look at two examples based on which we are going to solve using the approximate method. So, before we start discussing the examples, let us look at the variational formulation of plate dynamics. Till now we have not discussed this variational formulation. We have discussed only the Newtonian formulation of plate dynamics. Now, this variational formulation is a little cumbersome for the plates. So, let us see how it is, at least how it is formulated, but then if you go through the variational formulation of plate dynamics, then you will also see that the boundary conditions are obtained naturally in the process. So, you can cross check that the boundary conditions that we have discussed based on the Newtonian formulation and based on von Karman's boundary condition for free edge, you can obtain them directly from the variational formulation. So, let us start with a little bit of discussion on the variational formulation for dynamics of plates. So, let us consider a plate now here. So, when we do the variational formulation, we first write down the kinetic energy of the plate. So, the kinetic energy is for this little element is given by 1/2. If rho is the density, then dx dy dz, where z is the coordinate perpendicular to the plane of this figure, that is plane of the paper. So, this is the mass of this little element times its transverse velocity square. Now, in addition, if you also have if you want to consider the rotary inertia, then you have, in addition to this, 1/2 rho. Now, this is the this is the mass times z square. So, mass times the distance from the neutral plane square. So, that will give the moment of inertia of this little element at height z from the neutral axis times the angular velocity square. So, now angular velocity can be written as in the y, it is written as del w del x del del t of del w del x whole square So, this is the contribution from the rotary inertia, and if you now integrate this over the complete volume of the plate, then we can obtain the total kinetic energy of this plate. Now, since this field variable tracks the transverse displacement of the neutral plane of the plate. So, this is independent of z, and if the density is uniform etcetera. So, with all those nice conditions. So, there is nothing in the integrand that is function of z. So, z can be integrated out and written So, z goes from minus h by 2 to h by 2. So, this z coordinate goes from minus h by 2 to h by 2, where h is the thickness of the plate. So, then if I perform that integral, I can simplify this expression. So, is the integral over the area now of the plate. So, that is the kinetic energy. Now, this I, which is the moment of inertia of per unit area, so that is the moment of inertia per unit area of the plate. Next, we will write down the potential energy expression. Now, we have considered that this little element is subjected to in plane stresses. So, if you have this in plane stresses, then the strain energy stored because of the deformation is given by half times stress times the strain. So, now we have the normal stresses times the strain in the x plus normal stress in y times strain in the y and plus 2 times the in plane shear stress and the corresponding shear strain of the element. Now, this is per unit volume. So, now I have to again integrate the thickness goes from minus h by 2 to h by 2 and x y go over the domain of the plate. Now, here I have to finally obtain these expressions in terms of the displacement field variable, which is W. So, to do that, we first write down the constitutive relation, which is the Hooke's law. From Hooke's law, we can write, we have seen this before. So, the stress, normal stress in terms of the normal strains in x, similarly in y, and the shear stress in terms of the shear strain. So, if you use these expressions in the potential energy and of course, we also have to write these the strain displacement relation, which we have also written out before. So, from the displacement kinematics, so we have seen these expressions before. Now, so we will substitute these strains in terms of the displacement field variable in here, and finally, the stress terms will be put here. So, if you do that and make the final simplification, then upon integrating over the thickness direction, so this is the expression of the potential energy, the strain potential energy, where this d is here, of course, E is the Young's modulus and nu is the Poisson ratio. Now, so with the obtained expressions of kinetic and potential energy, we can now write the use the Hamilton's principle to derive the equation of motion. So, Hamilton's principle says that this variation must vanish. So, we have these expressions of the kinetic and potential energy, and if you want to derive the equation of motion, then you must follow the procedure that we have discussed in case of other structural elements like strings, membranes, etc. So, this will closely follow that of the membrane, only the terms are more complicated complex here, and because of that the procedure is straightforward, but cumbersome. So, one can derive the equation of motion, and the boundary conditions are also obtained along with this. So, that is the advantage of using the variational formulation. So, now using this, then we can also use the discretization using Ritz. So, based on this Hamilton's principle and Ritz expansion. So, Ritz method requires the Ritz expansion plus the Hamilton's principle. So, these two lead us to the discretization of the dynamics.